Welcome to Lecture 2B. I'm Tom Stephenson, and today we're going to be continuing on with our subject of foundations. So in this lecture we'll be looking at foundations more closely. Particularly we're going to be looking at damp proofing and waterproofing, as well as some more information on footings and foundations. If you didn't see Lecture 2A, go back and review that. That's a good starting point, so you know what we're talking about in this section here, and I'll give you a better perspective. So we want to identify the different methods and materials that are going to be used to construct foundations. We're going to be looking at piles and caissons, some special situations. We're going to be reviewing underpinning, how do you lower an existing foundation. So those are some of the topics that we'll also be discussing today, and we'll move on it. So piles and foundation design. We talked about soils having the proper bearing capacity. Well, in some cases it doesn't have the proper bearing capacity, and so in cases like that we have to find ways to support the foundation. And one of the ways that we use are piles and bearing piles. And bearing piles basically could be wood, it could be concrete, it could be steel that's driven down into the ground until it hits generally bedrock that it can support the actual weight of whatever the structure is. You see it very commonly used in large buildings, but sometimes you see it on houses as well, where there's an issue with support. And certain climates you might find that you need bearing piles in a lot of locations. I know in the area of Winnipeg, the soil is very unsteady, and it tends to heave a lot and move a lot. So even for a concrete slab in a community center, there might be a number of piles that would be driven into the ground to support the slab and to ensure that it doesn't move. And in fact, the slab is usually suspended off the ground because it's more concerned with the heaving of the soil than the settling of the soil. So there's a lot of different soil conditions that you run into in construction, and a lot of differences in geographical areas too, where one thing that's common in Toronto might not be common at all in Winnipeg, and vice versa. I remember when I looked at this community center in Winnipeg, I was kind of shocked by the number of piles that was supporting the slab, because typically we wouldn't be doing that in our geographical location unless there was some special soil condition. It could even be in that particular area where that condition occurs, that particular lot, and that would require that. You have bearing piles. Friction piles are another type of pile. Both are driven into the ground. They can also be drilled out and filled with concrete. So there's different mechanisms for doing that, or caissons. So friction piles are driven into the ground. Instead of it going down to bedrock, it's relying on the friction of the ground around it. If you've ever tried to take out a fence post and pull it up, and you rock it back and pull it up, very, very difficult because the friction of the soil is against it. So it's got a lot of friction, so that prevents it from being pulled out too easily. Well, it's the same friction that prevents it from settling too easily. And so engineers can design friction piles based on the soil type, the depth, and the surface area of the pile to have a good understanding of what kind of weight capacity it can support. So the advantage, of course, of a friction pile is you don't necessarily have to go all the way down to bedrock, because bedrock could be quite a distance down, and that would be very expensive to drive those piles that far. And so in cases like that, a friction pile could be designed instead of a bearing pile. Soldier piles, another different type of pile, and we see it everywhere in Toronto for sure, but in urban centers typically you're going to see it, is, you're excavating for a large building. Well, what holds the ground up, right? So what stops the ground from caving in along the sides, and what stops it from taking maybe other buildings that are nearby as well? Well, soldier piles are driven into the ground, and instead of them supporting basically weight, compressive loads on top of it, it's supporting lateral loads against it. And if they're deep enough, they'll also have tiebacks that are drilled into the side of the soil surface to prevent it from pushing inward. Typically you have steel supports, and then you have wood lagging that goes in between to support the actual, it's actually acting like a retaining wall, if you will. That can be used in commercial applications, but it can also be used in residential applications. What we find is a lot of the properties where we're doing an infill house, they're pretty close where we want to build the infill house to the next property. And usually a new infill house is going to go a lot deeper than, say, an existing house that maybe was built 60, 70 years ago. And 60, 70 years ago, they didn't usually think of basements as having living areas so much, or 80 years ago, 90 years ago. Some of the basements, you know, in older houses are like 6 foot high. So your new house might have a 8 foot, 9 foot, 10 foot basement. That means it's going to be a lot lower foundation. So if that foundation is a lot lower to the one next door, then this weight, when you excavate down, it could put that house in jeopardy, because that could crumble the soil. It wouldn't be able to bear that capacity. And if that starts to settle, that house is in jeopardy. So to protect that, in some cases, you might have to put a row of soldier piles and lagging to prevent any settlement of the property next door. So there's different designs that are utilized that way. So soldier piles is used for that in that example. So helical piles, those are also used a lot. So they're actually drilled in, and it's calculated how much, it's almost, they look like a drill bit basically. And they're actually calculated to support the loads above. They can be installed pretty readily, and can be used for remedial work, a building that's settling. They can be used in new construction as well. So different types of materials can be used. You see very often steel being used. Timber can be used. I see timber being used a lot on docks and near water and that sort of thing. Can be driven into the ground as well to support structures. So it just depends. It can also be drilled and filled with concrete. In this case, you got rebar sticking out of it, ready to tie into the building that will be structured on top of that. There's your soldier piles. This was for a condominium project down near Eglinton and Bayview, near Sunnybrook Hospital, multi stories. And you can sort of see, so you can see the piles, you can see the lagging, and you can see the tiebacks. So these are drilled into the side, and then there's a crossover beam that's put in place to, again, support and transfer the lateral load, so that this, because this is going to continue to go down. You can see the excavator, it's going down multi-levels because it's a very large condominium. I think it had like 3 underground parking garages, levels of underground parking when it was complete. The other thing that we can do, as I mentioned, we can underpin a existing foundation if we need to lower it. So I said that some older houses, they don't have a deep basement. Well, today, the value of a property could be drastically increased by increasing the square footage of the livable area. So a basement is a prime target, especially in an older house. If the basement is, say, 6'6", you could lower the foundation 2 feet. Now you've got an 8 foot or 8'6" ceiling height, and you usually have ducts and different things in the basement, but it'll still make it a nice livable area compared to the older basements with not very much headroom. There's no point in finishing the basement if everybody's got to be crawling around trying to duct around the ductwork and piping. So you can't excavate underneath an existing foundation completely because it would just collapse. So what we do is we actually measure around the foundation, and we do markings. So we'll do like 1, 2, 3, 4, and usually at spacing of around 2.5 feet to 3 feet. So the facing's usually around like that wide, and you excavate out underneath the foundation. You get an engineer to do an engineered set of drawings for the underpinning, and you follow their diagrams very carefully. This is very serious work. If you mess it up, the house can collapse very quickly. So you want to make sure that you do it well so that it's able to support the loads above it. Every year you'll read in the newspaper oh, this house collapsed, they were working on it due to underpinning. And when that happens, it's not a good situation. So you want to follow it very carefully. You would excavate under all the ones. So that would go all the way around the house. Let's say if we're lowering the entire basement, you would excavate all the number ones. And what you would do is you would typically chop this part of the footing off, and you would form this up with formwork, and they would all be excavated underneath the footing. So you do this usually by hand, so it's very labor intensive. And then you form that up and you fill concrete in all the number ones. Typically you'll let it dry with a little bit of a space, and you'll pack a non-shrink grout in that space, because concrete shrinks a little bit typically, so it'll shrink a little bit. So what you do is purposely leave a little bit of a space, and you pack in a special, it's a non-shrink grout mixture, which has a high compressive strength that is actually tuck pointed into that space right the way back. And then that, when it dries, it won't shrink, and it will take on that bearing load from above. So underpinning is a good way of gaining a lot of square footage. You know, if you've got a 2,000 square foot house, 1,000 on the first floor, 1,000 on the second floor, and you do this to the basement and renovate it, you've just added another 1,000 square feet, which can add a lot of value, even though this is a very expensive process. So all the number ones are done, and meanwhile, you know what you're doing? You're excavating all the basement floor. So while you're waiting for the concrete to set up, you're excavating the basement floor. So you got lots of work to do, trust me. Then you're doing all of the number threes. So you do all of the number threes all the way around, and you let them set up, and you put the non-shrink grout in, and you're still excavating the floors. Then you do all the number twos, all right, all the way around, and then you do all the number fours all the way around. So you do it in stages, and so there's days apart where you're laying the concrete set up and you're putting in the non-shrink grout before you're taking out the next excavation. So the house is well supported everywhere, because it has the capacity to span these short distances that you're excavating under. But very labor intensive, very expensive. You know, it could cost, the underpinning process could cost easily $50,000 to $100,000, and then you've got all the other issues. You got the issues of changing the ductwork, changing the staircase, maybe problems with headroom and different things like that you have to deal with in the design, as well as finishing the entire basement. But as I said, you add a lot of square footage. That money could easily be recouped in the new value of the basement. A lot of people may do it too, to add a basement apartment. So you'd have to get the proper permit processes like we talked about. You might have to get zoning changes and other issues rectified to do that. So there you sort of see a section detail, and you can kind of see. So this is actually excavated out. So this is a little bit on the rough side. On the back side, be on the smooth side, you'd have the formwork here. And then what's done is a weeping tile is placed around the inside, and there would be a drainage layer that would come down the inside of the wall and underneath. And so that if any water or moisture leaks inside the wall, it would come down and go in the inside. Because you're not damp proofing. With this method, you don't have to excavate the outside. So that saves you a lot of work. So in this particular case, you would run a drainage layer on the inside, because there'll be also a lot of cold joints. Cold joints are where the concrete joins up between other concrete here. And that's obviously potential for leakage too. But by putting a drainage layer, and we'll talk about a drainage layer and show you some pictures later on, a drainage layer improved for interior work, that alleviates the problem of the cold joints. So that can be quite a strong methodology to use, and any excess moisture that comes will be taken away with the drainage tile or the weeping tile that's placed on the inside. So that's giving you an idea of lowering a basement. I should mention there is another methodology, which is benching. Benching is you don't dig underneath the existing footing. You actually build out a bench. So if you want to go down, 2 feet, or let's say you want to go down 10 inches, all right? 10 inches, then you have to come out with the bench, usually more than 10 inches. Usually it's like a 7 to 10 ratio. So if you go down 7 inches, you've got to come out with the bench 10 inches. If you go down 14 inches, you have to come out with the bench 20 inches. And the reason for that is the forces coming down on the wall don't come perfectly straight down. They actually come outward. And if you just excavated this straight out or under the whole foundation and you left this underneath, then the house would collapse. So if you're going to put a bench, you have to leave this angled out, and then you have to put a concrete, literally bench or box here, and that prevents the wall from settling and pushing out. But you don't have to excavate underneath. The downside of that is you lose all of that space, right? So you lose all of that space on the interior. So as much as it's cheaper, if you're going that far with it, generally on a residential application, it's worthwhile to actually underpin the house because it gains you so much more effective floor space. So window wells, you'll see, are where you have a window in a basement and you're struggling to have it high enough above ground so that the moisture doesn't become an issue. So very often designs today and barrier-free access, making it more accessible for people in wheelchairs and that sort of thing. It's very helpful, say you're building a bungalow, to have the first floor fairly close to the ground, maybe a couple of risers up, and you can easily do a ramp to that. But when you do that, it means the window more or less has to, for basement windows, it has to be more or less below the grade. And in cases like that, you want to utilize a window well. So a window well is like a box that's placed around the outside of a window. It has to have a drain in it, all right? So basically the drainage pipe goes down, and then that would hook up to the actual weeping tile, and then this is all filled with gravel so that it's easy to, any extra moisture to find its way down to the weeping tile. The goal is not to have moisture gather around the foundation. Like we said, that's why you want it to slope away. And to, if it is going to gather at any one point, to make it easy for it to get to the weeping tile and then be taken away. You don't want a lot of moisture gathering around the foundation. And you certainly don't want this to clog up. You could have a massive rainstorm and this becomes like a swimming pool, and then it just comes through the window. So that can be a problem. So on a section view looking at this, you can kind of get the idea. So this is a section view and you're looking at it at the end and you're looking straight at it, and you can see sort of the connection point that's going into it. And it's a perforated pipe, so it'll absorb any moisture that will come in. So it's a typical weeping tile pipe. So there's the plan view of the window well that would be typically shown on a construction drawing. If you'd see that, then you'd know you'd have that window that would have to be below grade. And the window, I'd have to double check the Ontario Building Code, has to be, if it's less than 8 inches, it's either 6 inches or 8 inches, then that's when you require a window well. So if it's less than 6 inches, let's say, to the grade, you have to put a window well to protect that against moisture and snow buildup, etc. So some examples here, you can see the windows. These are partly above, mostly above ground, but the bottom of them will be below ground. And this isn't finished grading. This is the exterior drainage layer, this black here. And this will be graded away from the property. And so this is a protection around the window. You can see another one that's placed over here. So when we talk about foundations too, foundations aren't typically smooth. They can be stepped. We talked about stepping in the last lecture, so the grade is stepping in this case. And in this case too, you've got a wood frame floor that's going to go into this area here. There would be a sill plate that would be placed here. We'll talk about this more when we get into framing, but you have to form this out. So on the drawings, it would show something like this, and that would mean that that's got to be left as a cutout so that your floor framing could fit in here, because in this section right here, this would be the sort of the entrance from the garage. It's sunken. It's a couple of steps, or one step, 2 risers lower than the main floor. And so it's not, the main floor is going to be resting on the foundation wall here. And over here, you're going to have the sunken part of the floor resting on this edge here, where you'd have a plate placed, and then the floor joist would go on top of it. Another example here, just illustrating where that would occur. So you'd have essentially, you'd check the foundation wall if you have to have a cutout in this particular case for the foundation wall. Also, in this section here, you see that there's this little dashed line here. This stands for reinforcing rods. And the reinforcing is placed to stop this wall here, because the stairs is here, is considered laterally unsupported. So to ensure that the wall is nice and solid, we put some rebar in this section. The rest of the wall doesn't have rebar. This section that's lowered and this section with the stair has rebar, and particularly the area where the stairs is what would be termed in the building code laterally unsupported, because the floor is not against there. You just got a staircase, so the staircase isn't helping. A floor, you know, anchored to both sides of the wall, if you got pressure on one side, it's pushing against the other side, so it's really strong there. That's what we call laterally supported. If it's not, like where there's a stair opening or where there's a very wide window opening, so if you have a window that's beyond a certain size, like say 32 inches, if it's wider than that, then you have to have rebar to strengthen that wall, because the ground pressure against it could cause it to crack or could cause it to potentially collapse if it's enough pressure. So in this case, that rebar is shown here on the inside towards the house side. So you can sort of see it's more closer to this side than that side. Concrete is very strong under compression. Very strong under compression. It's not strong at all under tension. So that's kind of its Achilles heel, is tension. Steel is very strong under tension. And steel and concrete work very well together. So when you put concrete, it's vulnerable to tension. So if we had ground pressure pushing from here that way, right? It's pushing from here that way. What would the inside of this wall be under? Would it be under compression or tension? And if you said compression, you'd be right. So, you know, you're pushing against it. This side would be under compression. That side would be under tension if you're pushing against it. So where there's tension, that's where we want the steel. So that's why the detail drawing here shows the steel much closer to the inside. This is the garage slab over here. And so that's providing strength in the concrete where it needs its most. And so that's why it's saying laterally unsupported. That's a building code term. Laterally supported means, you know, the joists are against it, it's anchored with the plate, it's not going anywhere. Laterally unsupported means you need to have extra protections in place. And that's a good idea that you start to understand that. Like if you're looking at a set of construction drawings, I'd be looking where there's big window openings, where there's staircases, for rebar. Oh, where's the rebar got to go? Because I know in my head it's laterally unsupported, so there should be some rebar going in there. A lot of times in house foundations, they're not reinforced concrete foundation walls because they're usually not going deep enough, or there's usually not enough loads, unless there's some other soil condition that requires that, like an engineered pad that you're building on. So you're always looking for where you might have to place rebar and making sure that you put it in, because it could be missed, and that would be not a good thing for your foundation. So here's sort of that cutout that we're talking about in a foundation wall. So this would be what we call like a negative reveal, and so that would be cut out backwards here so that the sill plate for the floor joist can rest there, and then the floor joist, your structural floor, rests on top of that. So now we'll talk a little bit about damp proofing and waterproofing. And if we look at part 9 of the NBC and the OBC, a foundation wall must be waterproofed if hydrostatic pressure is present. So hydrostatic pressure is basically a wall of water. So that wall of water against it puts a lot of pressure against the wall. And you have an idea that hydrostatic pressure would be present if you're excavating and your excavation starts to fill with water. Then you know that you're digging below the water table, you've hit an underground stream or something of that nature, and that would mean that you're going to have to waterproof your walls. If you're excavating and the excavation is not filling up with water, then that's a good indication that that's not an issue in that particular case. Of course, there's different areas where you can have different things occurring during different times of year, and so some of those designations might come into play too that might require you to waterproof. If the idea of waterproofing is that you're making it almost like a bathtub, and so you're trying to protect that water wouldn't get into the basement. The other thing is you're trying to make sure that you're getting water away from the foundation, so that's going to usually entail waterproofing, a sump pump that's going to pump the water away, because you got to relieve the pressure of the water, because if the water is coming up from underneath, it can actually even lift floor slabs if you have it really tightly sealed. You want to relieve that pressure underneath, and the way you do that is with a sump pump. And a sump pump's kind of like this pit that you build, and you put a pump in it, and water finds the lowest location, and then it pumps the water out of it. Damp proofing, on the other hand, we just want to make sure that water can't easily get into the foundation. And so if there's a buildup of water, usually after a storm and that sort of thing, you want to be able to protect the foundation against that. So the type of coating that's approved for damp proofing is different than the coating that's approved for waterproofing. So usually it's a bituminous coating, a spray-on sort of tar coating that is placed against the foundation wall, and then a drainage layer is placed outside of that to allow the moisture to quickly drain down to the weeping tile, and the weeping tile to take it away to the storm drains. So damp proofing typically is much more common in residential construction, but again, it depends on the lot, depends where you're located. If you're building near a lake or something, the water table is going to be very high for sure. You're building at the bottom of a hill, very likely that there could be a high water table there. So in this case, when we do a poured concrete foundation, we did say that's the most common way of doing it. Those snap ties, if you remember from the last lecture, that are placed in the wall to hold it at a certain size and distance apart from the forming, those are snapped off, and they leave a little bit of a hole, and there's a piece of metal that's stuck in the wall, but the metal's a little bit below the surface because there's an indentation that when it's spun around, that'll break below the surface. Then you have to go back and you have to patch it to ensure that moisture won't travel across that snap tie and start leaking into the basement through those locations. So that those all have to be patched, right? And you can kind of see they've gone around, and if you can see sort of the finished grade markings there, they've gone around and they spray painted lines against the walls, and that's the finished grade. So if you remember from the site discussion we talked about in lecture 1, the site plan gives the finished elevations based on a benchmark, and so then these are marked so that they know where they're going to grade, backfill up the ground to. And then they'll of course have those slopes away from the houses, just swales, etc. And at the bottom here you can see there is a weeping tile that's been placed, and that weeping tile has a nylon sock, we call it, that's placed over it, and that's to stop the sediment from finding its way in and clogging the tile over years. The tile will be covered with gravel, and then backfill material will be put over that. So the weeping tile that's in the sock looks like this. It has all these serrations in it, and that means that when it's placed around the footings and moisture builds up through the filtering through the gravel, it will be able to take that moisture away, and then this connection here is actually connecting up to the storm drain for the house, and the storm drain is going to go into the drain on the street and take it away. In this particular subdivision, it was engineered that stormwater from the roof would go into a separate drain system, which would go into the storm drain, and then eventually that's going to come out through the tributaries, as you saw from the previous lecture, because this is the same houses that we were looking at in this previous lecture, same subdivision. This is your bituminous coating, which is your tar coating that's placed on the outside of the house. And you notice where the garage is, they don't place it, but inside the garage they do, because they don't want any moisture that might be getting into the ground from underneath this garage slab to leak through to the basement. So that's where the actual damp proofing goes between these points. And so you can sort of see around here, they've actually put a drainage layer around here. And you can sort of see there's a key in place along here, and that's when they're gonna backfill this, they're gonna compact this, they're gonna put a gravel base underneath it, and then there's this key that will tie the concrete floor into the walls so that it doesn't settle. This is the drainage layer I've been mentioning. There's all kinds of different manufacturers. When I talked about the underpinning and I said a drainage layer going on the inside, it would be a similar material. It's just different that it's approved for interior use. But what it does is these little bubbles hold the drainage layer a little bit away from the wall. And if any moisture happens to get through the drainage layer, through some of the joints and seams, it'll quickly fall straight to the ground, below ground, down to the weeping tile, the base of the foundation down to the weeping tile, and then it'll be taken away. All right. So, and these are for the rainwater leaders. So this is your system here as an example, and your weeping tile is a different system. So this is going on top of the footing. The weeping tile goes beside the footing. Very often this is not used, the piping system. Very often what municipalities want is that water to drain out onto the surface area and be absorbed by the local ground. It's less taxing on rivers and lakes and that sort of thing. Anytime you can get the local ground area to absorb the excess moisture. So waterproofing, as I mentioned, hydrostatic pressure, it can pretty much move anything. Like it's got a lot of power. It's why we've got to do our formwork really well, as I mentioned, because when the concrete is very plastic, it has a lot of hydrostatic pressure that it puts on it. Once it starts to set up, there's no pressure. But when it's being poured, there's a lot of pressure. And so it can actually put pressure on your walls, on your floors, and waterproofing has to have methods to seal this, but it also has to have methods to reduce the pressure, particularly upward pressure that comes from up above. But new walls that are formed and you do the foundation walls, you have to make sure that you put temporary bracing on long walls, because if you don't, when you backfill that, and say it's pouring rain and the backfill is very wet, then there's a lot of hydrostatic pressure against the walls. And if you don't have the floor joists on the top yet, then it's not laterally supported. And if it's not laterally supported, I've seen where the walls collapse. So you want to make sure that you put plenty of temporary bracing, particularly on long, straight, high foundation walls, because that are what we'd call green, not properly cured yet, because they're very vulnerable. And what happens in construction, to be honest, people get away with things. So they do it lots without putting any bracing, and they get away with it. Maybe the backfill was pretty dry, right? Didn't pour rain on it, and there weren't conditions that created the pressure. But then after doing maybe 15, 20 houses, you do one and it's very wet, you backfill it, somebody runs a bobcat along the side or the edge, putting more pressure on it, and then the foundation wall cracks, and not only does it crack, it shifts, and then you got one heck of a big mess to deal with. So you got to respect hydrostatic pressure, and you got to make sure that the amount of time that it takes to put bracing is hardly anything. So in an hour, a good carpenter can have the whole thing all braced up, compared to the days and thousands of dollars it takes to fix a foundation that's settled. So it's being proactive and preventative in those cases. So this is actually the foundation for those Doncaster drawings that are in your textbook and that we looked at the site plan for. So this is that site plan where it was already graded and everything. It was all nice. This is the foundation when it was being constructed. It poured rain on it. It was kind of a mucky mess at this point. I think it was early spring, as I recall. And it is a step foundation over here because remember the grade stepped a certain amount over there, so it fell off. There was that embankment from the last video lecture that we did in chapter 5. So this is what it would look like, and you can see the keying in place. This is where the porch would be. This is where the garage would be. This is the living area. The kitchen's up over above this, the next floor up. So you're trying to visualize things. That's what I'm trying to get you to sort of think about when you're given a project. The first thing I want to do is I really want to visualize what exactly is going on this project and come to some understanding of it. So drawings are very helpful for that, to visualize what you see. It's very, very helpful, but you got to also remember drawings are not perfect. There's an old saying that the map is not the territory. You know, the map is not the territory. You don't know, you can have an idea about Toronto by looking at a map, but if you actually walk the city, you'll really have a good knowledge of it. So yes, you've got to look at the drawings, you got to visualize it, but you got to really sort of visualize a lot of things, and you got to walk the site and understand the nuances of the site, look at for any possible constraints and issues, and have foresight in your thinking. If you're going to be a project manager, you got to be pulling all these kind of things together. So it takes time and it takes effort, but it's something to remember. The map is not the territory. It's good, can be good, but it's still got its limitations. I think there's been people that have driven off cliffs following a GPS, right? All right, so, and you'll have in your drawings, you'll have construction notes, or you'll have a set of specifications that you'll need to look at that will give you detailed information about the foundation. In this particular example, it's telling me the thickness of the wall. It's telling me the strength of the concrete, 15 MPa, megapascals, 2,200 PSI, pounds per square inch. Of course, in Canada, we're dealing with both metric and imperial, so we got to get used to dealing with both. Concrete strength, bituminous damp proofing, that's that tar coating that we were talking about. And then it says mineral fiber insulation, nobody does that. Or equivalent drainage layer, everybody does this. That plastic beadboard that you saw going around the outside, that's what that's referring to. Nobody in at least our geographical area really uses this that I've seen, but this is what's popular. It's pretty easy to put on. It tells you the size of the footings. It's 480 millimeters wide by 155 millimeters thick, or 19 inches wide by 6 inches thick, same thing. Then it says, or 600 by 200 for party walls. Well, this is not a party wall, so it would be, this is our size. Party wall is a wall that separates townhouse units. Continuous keyed concrete footing, that was that little slot that we saw that was put in there, as per soil report. So the soil has to be checked. There's an engineer's report on the soil report. If there's a problem with it, then it might be quite different. You might have to reinforce the footings, you might have to reinforce the walls, or do preparatory work on the actual pad that you're going to be pouring the footings on. So that supersedes. So this is just if it's fine, you've got the bearing capacity for the house, then the soil report would confirm that. Weeping tile going around the edge, we know where that goes. It always goes at the edge of the footing and it goes around the house. Gravel gets placed over the weeping tile and around the weeping tile. And then this is for the concrete slab. This would be for your basement slab here. So 15 megapascals, 2200 PSI. And then it says slab, 100 millimeters, 4 inches with crushed stone with damp proofing, and 25 MPa without damp proofing. What that means in that case, it's not talking about damp proofing like a tar coating. That's talking about, this is the basement slab. It's talking about laying plastic underneath the slab. And I'll talk about that a little bit more when we get to chapter 10 and we look at sort of concrete and finishes and that sort of thing. So that's that drawing for that house that we just been looking at, as I was saying. So the map is not the territory. You can sort of see that the porch is here and the garage is there. So this is turned around a little bit. Well, actually, it's right on. The porch is there and the garage is there. That's the foundation. The foundation wall is following this all the way around through here. This is where that cutout is that we were looking at for the sunken laundry area as you enter through the garage, because the next floor plan would show you entering through the garage. And this is where your floor joists are going to be placed for the first floor. The size of the floor joists are always shown in the actual foundation plan. So the technology of building our typical foundation is going to use concrete footings, concrete foundation walls to support the wood frame construction above it. Now, using a 3D model to look at this, you can kind of see right off, you've got footings, you've got column footings here, you've got a strip footing to support the wall, you got another little column footing with a strip here, and this is going to be, these two are, this is supporting, see the little cutout there for the floor joists above, that's going to be supporting that sunken laundry area that's above it. This is the garage. You can see that the garage is stepped because the basement, there's no basement, but the footings of the garage are not as deep as the rest. Now, this may or may not be true. If you're building one house, this would be absolutely true. If you're building in a subdivision, you might be excavating for 7 houses in a row. It's usually easier just to excavate them all at the same depth and fill this back in later on, rather than have this at one height and this at another height. But if you're doing one house, it's easier to excavate at the different depths and not excavate out anything more than you need to excavate. So different practices depending on whether you're building a row of houses or whether you're building one house. And of course, this only needs to be this deep because this will put you 4 feet below the frost line. Here, you're probably like 7'6" below the frost line, but you want a deep basement, right? These are new houses, so you're usually 7'6" to 8 foot deep, and some 9 foot and 10 foot on custom homes. So typical foundation wall detail that we looked at in the previous class, so you can sort of take a look here. So again, the brick sits on the foundation wall. The sill plate in this case is moved back so that there's room for the brick to fit on there. If it was wood siding or if it was any kind of composite siding material, manufactured siding material, the sill plate would be out here and then the siding would be over here. So that's usually the main difference. You have to have a ledge for the brick to sit on. Brick veneer on residential construction is non-structural. It does not carry the weight of the house. The weight of the house is supported by the framing members, not the brick members. Older houses in Toronto that are, say, and older cities are solid masonry, typically. So that usually means it's block and it's brick. In that case, they are structural. The wall is usually like 8 to 10 inches thick. But a 4-inch or a 3-inch thick brick wall is not going to be a structural wall unto itself. It's more for to protect against the weather, protect against lateral wind loads, and it looks nice and it lasts a long, long time. So with brick, we've got a minimum of 6 inches above grade building code requirements. You can see the gravel underneath the slab here, as I mentioned, the gravel over the weeping tile here, and the drainage layer material put down across here. And this detail, by the way, is a little bit older than the previous one. I noticed that this doesn't go all the way down to the foundation. Now they go all the way down to the foundation because we want to insulate all the way down. So this one's a little bit dated as codes continuously upgrade. So there's a bunch of key terms that we looked at. If you're not too sure of these terms, I would suggest you go back and you read the textbook pretty closely. There's a lot more illustrations and a lot more detail in the textbook that will help you better understand that. No live loads, no dead loads. Permafrost. Permafrost is where the frost doesn't go out of the ground. All of these are important points to understand. And we have this TACBOC detail here. I think this detail is pretty good because it shows a bunch of stuff going on with regards to why you might have to underpin. It's sort of thinking about through the soil condition issues. So in this particular case, we're stepping down. We're going to have like maybe a basement entrance, a basement apartment, separate entrance. And so as we step down, you're going to have a drain at the bottom so that basically this doesn't fill up with water and then leak in. And you'll see that it says 1, 2, 3, 1, 2, 3. And this means that that would be underpin that section. So here we've got the water. This would drain out. You would, the stairs is reinforced concrete. And this is stepping down over here. And the reason this is stepping down, because you got to maintain that 4 feet below grade. And then, of course, this is deeper. So we got to ensure that at no point are we less than 4 feet. Because if we are, then the frost can just get underneath this and heave this. Because at this point here, this is wide open. So the frost would go right through down here. If we only went 4 feet down from there, say we went to there, well, the frost would get right underneath there and start heaving everything. So we have to protect it that way. And the house where the doorway is, so this is the house where the doorway is, this has to be lowered too, to make sure that the frost doesn't go through here and heave up the area that's all opened up here. So like this would have to be 4 feet down here, this would have to be close to 4 feet, and then it'd be less, right? So but 4 feet from any of these points. So it could step up from there, your underpinning, if you wanted it to, till it's that far away. So that's why it's showing this is continuing past, and then this is continuing this far past, 4 feet from there. Also, you can, if you're checking this, this says section A. So there's a cut through line there, and this is a cutting plane line. It's looking this way. That means there should be a detailed drawing called A, section A, that's looking at this in that direction. Here, there should be a detail that's B, that's cut through and looking through that direction. So this is section A, where we're looking through and we're seeing everything cut through more or less at this point right the way through. Usually if they're really done well, they'll have an A here and then they'll have an A there, so you know exactly from where to where it's going. Here, because it's showing B, it doesn't actually go through this part, it just goes through the doorway. And that's where we're looking through. So we're the doorway, right through the doorway. This is sloping to the drain outside, and this is the interior. There's that non-shrink grout that I was mentioning before with underpinning that comes into play. Of course, you'd have some basement notes that you would also look at for details about concrete strength, size of footings, railings. All of that information would be in your general notes. So hopefully that's given you some applied examples, and then you should visualize it. And then if you see like a basement entrance, start thinking about, well, what would be involved with that basement entrance and how does it compare to this? So start visualizing things when you're looking at it. When you're looking at a wall, I want you to start thinking about, I wonder what's in this wall. And I wonder, is this a solid masonry wall or is it brick veneer wall? So we're going to be discussing these things as we move further and further through the course, and you'll get a good sense of it. So please take some time and go through the chapter and review the CMHC book, and we'll see you next time. So have a great, excellent day. Tom Stephenson signing off for now.